collaborative applications, some developments, work scenarios, and challenges related to this. Usually, I mean, if you Google it on the internet, you can write cobots and things like that, collaborative robots even. But from an industrial point of view, when we talk about industrial robots, we try to avoid the term cobot or collaborative robot, and in the future standards related to safety or in robots and robotics, robot systems, that term is taken out. But that will happen only in 1 year from now, actually, when the new updated standard is in place. But anyway, we talk about collaborative applications because basically almost any type of robot could work as a collaborative robot in a certain application, but then it has to be adapted for that. So let's go ahead and then we see how it could look like. So collaboration, then what do we mean really? We talk about a shared workspace between operator and robots or robot. Things get complicated or complex when we talk about many robots, one or many operators at the same time. That is almost never happening. So usually when we talk about this in action today, we talk about one operator, one robot. And then when we talk about shared workspace, we come back to that later on, possibly in another session as well. We talk about different kinds of shared workspace because it could be shared but not reached at the same time, or it could be synchronized. Then related to this, we have to make a risk analysis that will look at safeguarding the way things are programmed, the type of tool that the robot has, and so on. And that should meet all requirements for safe operation, of course. And the collaboration then introduces many added aspects of a work task, such as the speed of operation, lifting and holding support by the robot, for example, task sharing. The robot can move with precision and human take decisions based on complex information. So actually, task sharing is an important aspect of this, where they complement each other. And in this task sharing, the human-man interface is crucial. It's really important, so that the information is conveyed between the robot and the human in the proper way. So the control system of the robot knows what to do, how to react in a proper way, and the human the same. So the next few years then, what are we going to see? We are in what we call an Industry 4.0 next gen industrial revolution. Maybe revolution is not the right term here, but something is happening. It's a paradigm shift anyway, that we're moving into a situation which allows for more of artificial intelligence, more of autonomous operation, autonomous work tasks done completely by algorithms, controlled by algorithms in another way than was possible before. What we have seen so far is that machines, robots, whatever it is, processes, they have been controlled by pretty deterministic programs, so that in every state, in most cases, it has been possible to know pretty well how a process is going to happen. um, what is the robot going to do, what is the machine going to do, and so forth, with a few exceptions when we have sensor-based control. But anyway, that has been the norm. But that is going to change now. And we are moving also into this kind of thing, which is collaborative applications. Also, what is happening is that more robots, more autonomous or automated equipment will be simpler to use. We will see a diversified market in many ways. So they're used um, in more type of applications that are different from before, and global competitiveness and faster modernization of production equipment. So we change the old to new ones, and we will be able to produce with shorter product life cycles and increase demand of flexibility in production. And given this, I mean, the number of robots, for example, is increasing quite drastically. However, I mean, it's not big numbers in total, of course. I mean, we are far from that situation, but still it is increasing quite a lot. And especially we can look at the work task that the robot do is not only one shift, it might be three shift or even weekends. So and the robot might work faster and the human also. So one robot might work for three or four or five people, so to say. The operator and robot collaboration in production systems. So we talk about this co-work, and when we do that, we have to look at safety, of course. That is crucial, and the machine-human interface, and that has to be an effective and intuitive sharing of work tasks. And this case here, I mean, this is just a use case to illustrate what we talk about. So the human is actually combining the precision and holding capacity of the robot by getting and placing small components where they should be, which otherwise should be quite complex and complicated by a robot. And the mobility of the human is just outperforming any type of robot in this type of application. So this is quite a good example of how it could be with this kind of combined collaboration. But we come back to the issue of safety and some examples about how that could look like from perspective of what is possible when we talk about force torque control, safe control, and there are opportunities in autonomous mode control, so to say. So these movies are made by DLR in Germany, in Munich. They have a really good mechatronics group related to these kind of issues, and force torque control of an KUKA EVA robot arm. And this relates to some experiments related to human impact experiments, as you see here. And the controller detects the collision, and it has to have a gravity compensation because the measurement of the force is related to the impact of the body. But at the same time, it has this kind of gravity that it has to compensate for. so it knows what is the impact, what is the gravity, and so forth. And there are some limitations. I mean, how fast can you go without hitting too hard, so to say? That was in this case the maximum joint torque exceeding. And what is allowable or what is acceptable, this kind of experiment in reality should be much lower than this, of course. And especially, I mean, if you have something sharp in the tool, I mean, of course, that is super risky in this case. So that is nothing we can have. This is another experiment on the shoulder. And this is the highest velocity that this robot can actually go with, 2.5 meters per second, which is pretty much pretty high. And that is nothing that could ever be accepted. But for demonstration purpose and for research purpose, it illustrates how things can look like. But if you do the same type of thing with an industrial robot not intended for this kind of collaborative application, that would be like a killer, especially this kind of demonstration with collision to the head. Most robot really doesn't stop. This robot has a control system that has that kind of capability to detect and react fast. And that is nothing that anyone should do at home, really, or in the lab. For what reason? Because this is really dangerous or even fatal in most cases. Because moving with this kind of speed, I mean, in this case, 1.5 meters per second is really fast and really dangerous. You can also see that he has his glasses on. And I asked him, and he said that he really forgot. It could really have destroyed his eyes. So this is nothing one should do. But this shows anyway some quite interesting research in the area of collaboration, and that can be taken further. This guy Haddadin is currently working with the Franka robot that I will show later on. Some other examples related to research and development and related to skills are work related to virtual reality, augmented reality, sensors, deep learning, and artificial intelligence. And if we look at it in more detail, one can look at some applications or some work that we feel is really simple. And some people they ask, is it possible to do it by robots? Like this with close grasp point detection. So yeah, it is possible. And in this case, it's the robot PR2 costing something around 250,000 euros. Can do this. Now one have to accept that this speed of operation of the movie clip is much faster than the real application is performed by the robot. But it does it really. It uses stereo vision and scanning capabilities and so forth to identify what it is grasping, and then it can perform the task. So things can be done which normally is done by humans, but on the other hand, usually these kind of tasks can be performed by humans much better. and faster, of course. Can continue like this. And the other one is pretty interesting because that is how to make coffee using a coffee machine. And actually, what is done here is that the operations by the robot is done and programmed, so to say, on the fly, using the information how the machine actually works and models, uh, even also 3D models, how it is or it should be operated by the robot. And well, let's have a look at it. And it has sensors, so it can combine, so to say, the model-based information with the real information. So it's a sort of augmented reality, reactive um, programming, and the verification is done on the fly when it is working. So there are different types of applications here. Now it is instructed now how to turn on the knob for the lighting. It gets the verification when it do so, but it has a model what to do, so to say, and this way the robot can learn different things on the way, which it has in a model, and that is actually what Industry 4.0 is about. But this introduced virtual reality, augmented reality, and in real life uh, feedback to the model and the vice versa. So it's pretty interesting. So what's next then? This video shows some aspects of what's ongoing at the moment and what to expect. Turn off it. Two-armed robots has been ongoing for some time or some years. It hasn't taken off as expected, and in reality, a two-armed robot in one unit is a bit more expensive than two single-armed robots combined, which also could be formed in one controller. But still, in some cases, it creates some opportunities to use it like this. And the collaborative applications is supported by new developments of RobotDom that has inbuilt force sensors for detection of proximity of people or collisions. This is another example. The former one was Yaskawa, and the one before was from ABB Robotics. So this is Comau, an Italian robot company. So there are many developments relating to these kind of things, actually. In this case, it's the um, assembly or installation of a battery into a car, and it's supposed to be on the production line. In this case, where people are moving around. Now there are some implications related to this, and that is the speed of operation is usually much slower than otherwise. I mean, these kind of robots doesn't operate at 2 meters per second; they operate much slower. And in this case, the robot gripper was integrated with a sensor to detect the presence of a human. These are some other examples of mobile robots moving around, and also in a collaborative area where people could be around. This is actually interesting. It's a iCube. It's a robot for research in cognitive robotics, actually to learn how robots should learn things on the way, like a baby or a child does learn something on the way. So there are quite a lot of research and development in different things. This is this is a lightweight robot for to be operated and used at for electrical wheelchair for disabled people. To pick and place things or as an eating aid or whatever. This is a gripper like a hand, but the use of that one from Schunk is only in academics so far. Knowledge. This is kind of a demonstration of the capability of reacting to, in this case, a ball is coming in, and in reality, it's pretty simple because by that kind of data and the knowledge of what it is about, just to calculate that path from pure physics, so to say, and it works all the time if it's fast enough, and it is really. So this is just a research platform for different kind of studies related to control. And at the end, we have that robot PR2 again making popcorn and putting salt from a salt mill. And despite the amount of sensors, it still doesn't place it at the right place. So this is quite both interesting and challenging in a way. I mentioned that Franka robot, and that's an interesting development, actually based on the research done in safety before. I showed it the video before. And it has a controller that can react quite rapidly on detecting collisions. It has sensors in all the joints, so it knows what is, also it can detect what is happening and react on that one. And an intuitive use interface for programming and doing things. So, and the 7-axis operation, so it's pretty um, versatile in its operation for motion. Yeah, this is just an example how the robot is building it itself, so to say, more for fun, I think. But anyway, it shows what is possible. Move forward. So, just some discussions based on this. Lots of things are coming up now. Sensors, new robot types, software development integration, skills and artificial intelligence, augmented reality and virtual reality, and more. Uh, these things are happening at the moment. Sensors, which is interesting in this, is that there are lots of products out there that requires sensors. Take, for example, cars, which are supposed to drive by themselves. So a lot of sensors are in the development as we speak, and those sensors could easily be implemented in robotics as well, or machine lines, or wherever it is, and at the low cost, because they are, when they are developed and built in millions, they become cheap. And this is a new thing compared to how it has been before. New robot types, definitely, but most robot types has been developed and made as they are now, but there will be new variants, more specific for specific applications, of course. some variants that are more adapted for its use. It's a way to actually adapt to the customer needs. Software development is related to making things program easier and faster. And that will be combined with skills in AI and similar things, or the use of augmented reality in making program for robots to make it more fast and robust for the intended application. So things are moving fast here. So standards related to safety, when we talk about robots, are related to, in most cases, to these standards. 10 to 18-1 and 2, that is related to robots, and part 2, robot systems and integration, or integrated systems. And then there is a technical specification, 15066, safety of collaborative robots, which will be changed, as I mentioned, in a year from now, about that we, or the term collaborative robots will be taken out in favor of collaborative applications. But anyway, this is how it looks now. And then we have 13482, which is robots and robotic devices, which is related to safety requirements for personal care robots. They are not the same as industrial robots, but they are harmonized together in a way. And what we can see in the future is that it is blurred in a way, because if you use a robot used for services and you apply it in industry, it will become by definition as an industrial robot, and the vice versa. So in a way, it's going in both ways. Anyway, there are some collaborative scenarios: robot assistance for collaborative tasks, co-work. It could be robot assistance as a versatile tool in crafts. It could be robots with integrated process tools. It could be multi-robot cooperation as synchronized. It could be large work envelope manufacturing robots, large objects, shipyards, bridges, and so on. So the variation here is huge, really, how it could look like. But anyway, what we talk about is that we have the person here, we have the robot here, and it could be a shared workspace, but they never work together in the same workspace at the same time. Or it could be that they do that, but they never, so to say, collide or make a task that really is going together, or they are really working in the same work task on the same object at the same time, but really never touching each other, or they are synchronized. So the robot is, for example, holding the object while the operator is doing something on the same object. So it's really synchronized. So there are different variations and different complexity related to collaborative applications. And that really has to be addressed by the risk analysis and the type of way to set up the whole workstation. In this case, this is exemplified by safety scanners looking at this direction, looking at this direction, and this direction, and possibly there could be added sensors to look at the overhead type of optical scanners or whatever. So, I mean, it's really to identify the workspace, to identify the hazards, making a risk assessment, reducing the risk whenever possible, as much as possible, add some specific features like force and power limiting of the robot. So if there will be some interaction, it will be at a low force and power. And then also look at what is possible related to enabling devices, because in normal operation of a robot, the user has to enable a device for the robot to move, but that is not required when we fulfill all the obligations related to these things. But at the same time, the robot will move a bit slow. There are some challenges still, and that is if we use the thinking behind collaborative applications in the way it is intended, in flexible production, where we change things frequently, and we might even reconfigure the system. It might be the case that there has to be a new risk assessment, a new risk analysis, a new risk reduction related to this. And if this is the case, the CE marking might not be valid anymore. And in those cases, as pointed out in the standard, it say that in consultation with the user, the integrator, meaning the company, the system integrator that actually made the system from the beginning and made actually also the CE marking, shall identify and document the task associated with the robot cell, and then possibly assign a new CE marking. So this, of course, is a challenge and not really feasible in flexible production. Because if we talk about low volume production, we might want to change it every week, every day, whenever we like. And we cannot just call the system integrator to do these kind of things. We have to do it ourselves. And that knowledge should, if it is in place, we can do it. There should be no problem with that. And this means frequent change over between products. Could be every day, every fourth hour, whatever it takes. And it might call for some kind of system reconfiguration, meaning changes outside equipment flexibility that was thought of beforehand. We rearrange things. And that could be moving around the robot or other machines or other equipment or whatever that we didn't think about beforehand. So the needs relates to identification of hazards, doing the risk assessment, risk reduction, and look at certain configuration issues, because still lots of things related to a robotic system are based in software, PLC, controller, and related stuff, sensors, and we have to be able to generate those things quick and also verify the functionality and also related to the safety, safe operation. Otherwise, it's not related only to safety, but also the functionality as such. So, example of work scenarios could be, for example, inspection by naked eye of the operator. There are cases, for example, in nuclear business or in aerospace, that there has to be an inspection of things done, so to say. It could be welded items or whatever, has to be inspected by a naked eye of an operator. And a case could be that the robot is grasping and manipulating a workpiece that is to be inspected, and then shown by the operator at the places to be inspected. So in that way, we make sure that the operator is really checking the points of interest every time. Otherwise, we are not sure that has been done. But still, it is a sort of a collaboration where the robot is close to the operator, but not in contact. Another one could be jigless tack welding, supported by robots. So the jig is defined in software, meaning robot programs where a robot positions the plates to be welded. And the tack welding will be performed by a human welder So one or several robots are actually holding the workpieces, and the human welder is doing the welding, while the robots they are standing still, so to say, with the objects. So that will generate a faster preparation of new products, and customization of products will be possible at lower cost. A third one could be collaborative assembly. So a robot manipulates and positions heavier objects, and the human manipulates and assembles smaller objects on the bigger objects, so to say. So that is a true collaboration, but still, it could be made in a way that the robot is standing still in a static position under power. And this means that in principle, all these type of applications could be done by almost any type of modern industrial robot. It doesn't have to be what is called so-called cobots. It can be any kind of industrial robot. You have to remember that. So discussion based on this is actually related to the challenges, related to safety, related to, well, this is related to the standards. How does it look like? And the standards is under an update revision now, and that also relates to the machine directive that defines how systems should be designed and implemented, at least within the European Union, to be safe. And other stuff, of course, related to efficiency and opportunities in new directions. That is something we have to see in the future. Okay.